Hello, Allegheny College Introductory Astronomy students, and welcome to another Introductory Astronomy class with Bella the Cat and me, Jamie Lombardi. We're going to go ahead and cover Chapter 19 today, the last chapter in the book. And then on Monday, we're going to go and review. I picked out an astronomy picture of the day today from 2018 that's very relevant to what we'll be discussing. As you know, Chapter 19 is on life in the universe. And today we're going to be talking about satellites, including the one that's being launched here back in 2018, that look for exoplanets, that is, planets around other star systems. And so here, this is the Transiting Exoplanet Survey Satellite, TESS, which for the last couple years now has been scouring the skies for planets, and we'll get a little update today on how that's been going. All right, without further ado, let's get back into the chapter. You'll remember that last time we covered the first couple sections from Chapter 19, and now we're into the third section. We're going to talk about the potential for life around other stars. We want to define this word habitable. That means that the world has the basic necessities for life. It doesn't necessarily have life on it. It's different to say that a place is habited than it is to say it is habitable. If it's habitable, it means it could support life, but the life may not be there. So to have a habitable world puts constraints on the star systems that you're considering. First of all, you might expect the star system should be old enough to allow life to get a foothold. If the star was just born recently, perhaps then it's unlikely that life could exist on the planets or the moons of those planets going around that star. You would expect the planets need to have stable orbits, right? If the planet is going to be thrown out to large distances or thrown in, that's no good for life on that planet. If you have a planet inside the habitable zone, then liquid water could exist on its surface. If you have a planet outside the habitable zone, well, if it's too close to the star, it's going to be too hot for the liquid water. If it's too far away from the star, it's going to be too cold. The liquid water will freeze. Even so, with these constraints, there could be billions of stars in our Milky Way alone, which offer the possibility of habitable worlds. More about that habitable zone. Here's what it looks like for our solar system on the left here. Mercury and Venus, we know that they're not habitable. Too close to the sun, too hot for liquid water to exist. Earth clearly is habitable. In fact, it's habited. And Earth, the third rock from the sun, is on the inner portion of our habitable zone. Mars is on the outer edge. Remember that Mars did have liquid water on the surface billions of years ago. And so, although it no longer does, it's at the right distance from the sun where you could have water on the surface. Now, if you go to stars of smaller mass than the mass of the sun, those are not going to be as bright. We're talking about main sequence stars here. And so the habitable zone will be tucked in a little bit closer. The planet will need to be closer to that dimmer star in order for liquid water to be able to exist, in order for it to be warm enough for there to be liquid water. And if you went all the way down to a 1/10 solar mass star, that habitable zone gets tucked in really closely. It also gets smaller. And so these larger habitable zones are more likely to have planets within them simply because they cover a larger extent. Now, the TRAPPIST one system has become famous over the last few years. TRAPPIST stands for Transiting Planets and Planetesimals Small Telescope. It's actually now a pair of telescopes, one in Chile and one in Morocco. The Chilean telescope announced its first system, TRAPPIST-1, of a nearby ultra-cool dwarf star, so it's an M-type main sequence star with 3 rocky exoplanets around it. And this star is only 0.089 solar masses. Remember, below about 0.07, 0.08 solar masses, you get into the brown dwarf regime. So this is just about as low of a mass main sequence star as you can get. This main sequence star is 40 light years away, so it's relatively nearby. Remember, the closest star to us, Proxima Centauri, is just over 4 light years away, so this is less than 10 times that amount. Follow-up observations with the Spitzer Space Telescope in the infrared occurred, and in 2017 they were able to announce that there's actually a total of at least 7 rocky planets, all Earth-sized, orbiting around TRAPPIST-1. 3 of those planets are in the habitable zone, which is the largest number of habitable planets in a single system that has been discovered to date. So this diagram here you see compares TRAPPIST-1 to both the Jovian system on the top with its innermost Galilean moons, Io, Europa, Ganymede, and Callisto, and to our own solar system. Now, if you tried to fit TRAPPIST-1 and its 7 rocky planets all within our solar system, they'd all be tucked in well inside of Mercury's orbit. In fact, we've enlarged this by a factor of 25 to show you closer up what it would look like in terms of their orbits. And the statistics on these 7 rocky planets is quite remarkable. Look at their orbital periods, varying with the closest one from 1.51 days up to 18.76 days. Of course, the closer it is to its star, the faster it's going to orbit from Kepler's laws. The further the exoplanet is out, the longer it takes to orbit. And all of these distances are less than 1/10 of an astronomical unit, so it's really tucked in close. In contrast, Mercury is nearly 4/10 of an astronomical unit away from the Sun. And if you look at the radii, these are all remarkably close to 1 Earth radii. 1.12, 1.1.78. It's varying from 0.77 up to 1.15 Earth radii. And the planetary masses are also on the order of the Earth mass or less. You can see some of them are much less, 1/3 the mass of the Earth. This is impressive that you can get down to these low masses. And if you look at the densities, you can convince yourself then that these are not gaseous planets. The follow-up surveys by Spitzer and Hubble Space Telescope help to confirm this as well. The densities here are on the order of the Earth density. Remember, the Earth has a density roughly of 5 grams per centimeter cubed, and these aren't that dissimilar from it. One of them here has a surface gravity of 0.96 G. So you would only weigh 4% less if you were to stand on the surface of that particular exoplanet. So this is a remarkable system. It's got people excited that you could find something so nearby that has so many of these planets similar to our own terrestrial planets that perhaps there are a lot of these Earth-like planets out there. Now you may wonder, okay, what would life be like on these planets were it to exist? Well, it may in large part depend on what kind of star those planets are orbiting around. In the case of TRAPPIST-1, it was an M-type star, and the planets there, they might be black. There's no reason life would have to evolve to give you green vegetation. Here on planet Earth, green is in the middle of the visible spectrum, and life has evolved. Planets through photosynthesis has taken advantage of the fact that the sun is emitting in the visible and it's absorbing light from the visible, right? And it scatters away the green light because it doesn't need all the visible light. Around an M-type star, which is dimmer, perhaps the plants on that planet need to gather more light to be able to survive, to have the energy they need to live. And so perhaps you have black plants around M-type stars. Young M-type stars give off bursts of X-ray and short wavelength radiation while they're in their early stages of life and when they were forming. And so perhaps life there is underwater where it's shielded from those radiation. And you could imagine going to really bright stars, O, B, A, F type stars that are very luminous. Well, probably life won't be able to spring up around an O or a B type star because they only live for a few million years. And so that doesn't really give a lot of time for life to take a foothold. But maybe let's say you have an F type star, still very bright, much brighter than the G type star that's our sun. And so perhaps plants on that kind of planet around an F type star could be reflective. They got so much light shining on them that they don't need it all, and they can afford to scatter some of it away. These kinds of thoughts are coming from an article from Scientific American in 2008. Now, with the TRAPPIST-1 and other systems, it's a natural question to ask, well, just how similar are those exoplanets to our own Earth? And in fact, there's a way to quantify that. There's what's called an Earth Similarity Index, an ESI. And it's simply a number that's between 0 and 1. The Earth has an ESI of exactly equal to 1 because it's identically similar to itself. It is itself. And the number of 0 for an ESI would correspond to a planet that is not at all similar to the Earth. The closer the number is to 1, the more like the Earth this planet is. There's a nice little description on the Planetary Habitability Laboratory page that we can show you. There are different ways of defining this ESI. This is a rather simpler one. It just takes into account two main types of quantities that are being compared. The flux of light at the planet being considered, that's what S is, and the radius of the planet, that's what R is, compared to the similar analogous quantities, but for the Earth, that's when you have a subscript circle with a plus inside of it. And you can see if the S of the planet was equal to the S of the Earth, and additionally the R of the planet was the R of the Earth, you would get 0 inside this square root, and you just get ESI of 1. But if either of those quantities differed from that of the Earth, then you would get some non-zero, non-1, but between 0 and 1 ESI. The plot down here shows us what you would get for the known exoplanets. Each one of these dots is some exoplanet where this ESI has been calculated. The Earth would be right at the center. And in the middle of that blue region at the plus, you can see that the Earth has one Earth radius, well, 10 to the 0 is 1. It also has a solar flux, 10 to the 0 is 1. And so dots that are further to the right than this have more flux on that planet. Dots that are more to the left has less light coming from their sun. Higher up are the larger planets, lower down are the smaller planets. You can see we've mostly been determining and discovering, rather, larger planets than the Earth because they're easier to discover, not necessarily because they are so much more plentiful. Now, there are other more complicated ways to calculate the ESI that you could use if you have more of data available about your exoplanet. So we can take a look at some of the exoplanets that have the largest values of ESI, and you'll see that this is from the Wikipedia page. Nearly topping the list is TRAPPIST-1e, one of the exoplanets we were just discovering. There's only one higher, and that's actually an unconfirmed exoplanet. And so it remains to be seen whether or not that will be confirmed. But TRAPPIST-1e, that is in that system we were just talking about. And it's tidally locked to its star. Its ESI is 0.95. T-Garden B also has a 0.95. And you can see here that there are dozens on this list, but that the ESI numbers quickly go down to being close to 0. Like Venus, for example, has an ESI of 0.44, and we know that Venus is not at all hospitable to life. 900 degrees Fahrenheit day and night? No thank you. And so the point is that a lot of these on this list are likely not to be habitable just because they have an ESI which is large. That's not the same thing as saying that they're habitable. The ESI is measuring how similar they are to the Earth in terms of their mass and so forth. So to review, looking back at that TRAPPIST-1 planet E, you can see it has a surface gravity of 0.9, almost the same density of the Earth. It's just about 10% less in radius and 23% less in mass. Now, one big difference is this guy is tucked in close. A quote-unquote year on TRAPPIST-1e is going to be 6 days. That's how long it takes to orbit its star, right? But nevertheless, that is thought to be in the habitable zone. This is one of the 3 rocky exoplanets from the TRAPPIST-1 system thought to be in the habitable zone. Okay, well, this is something that we've started as astronomers to be able to do. And in the coming next few years, we hope to have more kinds of data to show you. But the hope is to look at some of these exoplanets, look at the sunlight, the starlight from the star it's orbiting around, shining through that exoplanet's atmosphere, and look for spectral lines that could be hints or signatures of life there. So, for example, let's imagine we did that with the planets in our own solar system, Venus and Earth and Mars. Well, on Earth, we've got a lot of carbon dioxide in our atmosphere. We also have water vapor, H2O. We've got ozone. The ozone in particular is an interesting indicator that life could be on a planet, because the way you make ozone, O3, is from oxygen, O2. And imagine some cosmic ray comes and hits an O2 molecule, breaks it up into an O and O, and each of those O's, or at least one of them, could find an O2 to make an O3, an ozone. That's how ozone is created. But to make ozone O3, you need to have molecular oxygen O2 around. And molecular oxygen, as we know, is what plants give off through photosynthesis. It's what animals take in as they breathe. And so if there's oxygen O2, then that could be an indication that there is life similar to life as on our own planet. So by looking at spectra of the planets, we may be able to get hints as to whether or not there is life on them. Now, finding Earth-like planets is hard. Recall back from Chapter 1 at the beginning of the semester that we said if we shrunk the sun down to the size of a grapefruit, the Earth would be the size of the tip of a ballpoint pen 15 meters away. And the closest star, Proxima Centauri, would be out near San Francisco, California in this scaled down model. Now imagine that you're trying to look to Meadville, Pennsylvania from San Francisco with a telescope. You're looking at a really large grapefruit representing the sun, and there is this little tiny dot orbiting around it 15 meters away that you are trying to make out. That gives you some level of appreciation for how difficult it is to detect exoplanets. And in fact, exoplanets are usually found through transiting. So the planet will pass in front of the star and you'll see a dimming of the star. We'll see a little bit more about that in a moment. Or from gravitational tugs, as we discussed earlier in the course. There's only a very small number of cases where planetary systems have been directly imaged. Fomalhaut comes to mind. In terms of nearby exoplanets that have been directly imaged, one was just announced within the last few days. Remember the Alpha Centauri system? It's 3 stars, including Proxima Centauri. That's 4.2 light years away, the closest star system to the sun. Well, Proxima Centauri has exoplanets around it. The first one discovered was Proxima b. Just recently, Proxima c was discovered, and now they've been doing follow-up observations. And in fact, although this planet still needs to be confirmed, there is intriguing evidence that Proxima c is going to be confirmed as an exoplanet. And furthermore, there's now intriguing evidence that it's been directly imaged. And so the light coming from Proxima C in one of their images that they took was 6 times brighter than the noise, which in principle could be a fluctuation. And in practice, if you look at the picture, you can't really make out with your eye Proxima Centauri C very well because of the fact that it is just a little bit above the noise. But with follow-up observations, the hope is that you may be able to get even better direct images. But here you can see there's an article from April 21st, 2020. I'm recording this on April 23rd, 2020 in Scientific American, talking about the first ever image of a nearby exoplanet. So we're starting to get hints that planets like the Earth, this one is several times the mass of the Earth, but planets we know are plentiful. And in fact, we're starting to get hints that Earth-like planets are plentiful as well. So are they rare or common? Well, in terms of their numbers, we're learning that yes, rocky terrestrial planets exist. In terms of them being habitable and habited, we're not sure yet. There may be a habitable zone within galaxies, similar to how there are habitable zones around stars, where life can get a foothold. If you're too close to the center of the galaxy, where supernovae are going off very often with sterilizing radiation that gets shot out, then perhaps you're not going to be able to have habitable planets in those regions, at least not habited planets. They may meet the definition of habitable in that water can exist on them, but they won't be habited because of the sterilizing radiation from nearby supernovae. And if you go out too far in a galaxy, well, perhaps there hasn't been enough generations of stars to eject heavy elements back into the gases to allow new generations to form. Life presumably needs heavier elements in order to exist. I can't imagine how life on planet Earth would exist without things like carbon and oxygen and even iron, for example. It could be that you need, in order for your planets to be habited, a Jupiter-like big brother. In the first few 100 million years after the solar system formed, Jupiter would scatter away the comets and asteroids that roamed throughout the disk through near the ecliptic of this newly formed solar system. And so those comets and asteroids would be sent to safe locations, maybe even into the sun or out into the far reaches of the solar system, where their orbits would be perturbed and they become part of the Oort cloud. And if Jupiter weren't there, maybe those sterilizing impacts from comets and asteroids would continue for much longer, and life wouldn't be able to spring up on places like planet Earth. It could also be necessary that if you want to have life on your planet, that you need plate tectonics. You need a geologically active planet. We saw how important the carbon dioxide cycle was. That's what this figure on the left here is reminding us about. How there's outgassing through volcanoes, and that carbon dioxide can dissolve in rainwater that flows down and gets deposited on the seafloors, and then subduction takes that carbon dioxide, which is locked up in rocks, and brings it back underground, perhaps making magma that then will outgas, and the cycle could continue. And to stabilize the climate, carbon dioxide cycle played an important role in that process. Perhaps if you didn't have geological activity, so there's no subduction, no outgassing through volcanoes and so on, perhaps you wouldn't be able to stabilize your climate. Perhaps life wouldn't be able to evolve there. The truth of the matter is, we really only know about life on planet Earth. So we don't yet know how important or negligible these concerns are that we're now discussing for preventing or allowing life to exist elsewhere. There are now over 4,000 confirmed exoplanets. Many of them, more than half, were discovered by the Kepler satellite. Its mission ran from 2009 when it launched up to just a couple years ago, 2018, when it ran out of fuel and was retired. And here, if we go to the NASA Exoplanet Archive, we can see a list of all of these exoplanets, right? All 4,152 of them. If we like, we could decide to search on those that were discovered with the help of Kepler, and you can see that there are 2,349 exoplanets. These are confirmed planets. This doesn't even include the candidate planets. And we can do lots of fun things with these data. I'll go ahead and sort these by planetary mass from largest to smallest. And so here's a big 22 Jupiter mass planet, 20. You can see many of the planets are Jupiter mass, right? 1 here on this scale refers to a Jupiter mass planet, Kepler 44, for example. And as we go lower and lower, we get to planets that are Neptune-like and ultimately Earth-like. Remember, Earth has a mass which is about 1/300th, roughly 0.3% the mass of the planet Jupiter. And so once we get down here to 0.05, that's a super Earth. 0.03, now we're getting right around Earth-sized planets in here. And this gives you a feel for just how many of them were discovered by Kepler. Several of these are in habitable zones, a growing number of planets, when you take into account all the different ways of finding them, are in habitable zones. Now, what Kepler did was it was in an orbit around the sun with a semi-major axis just a little more than 1 astronomical unit. So on March 5th of every year, the Earth would be here, and Kepler would drift a little bit further away with each year that went by. Both the Earth and Kepler orbited around the sun together. Kepler was pointed towards the Cygnus of Swan constellation. You can see the grid over which it was searching. So you're learning right now about the summer triangle, including Cygnus of Swan. There's Deneb at the tail of the swan. And not far from Deneb, you see where Kepler searched. This is in the plane of the Milky Way galaxy. The answer to today's reading quiz is phone home. Phone home. Hope you get it. The reason Kepler looked in the plane of the Milky Way was simply because it could then monitor many stars all at once for these transiting events. More recently, the TESS mission has been monitoring the skies. It's working under a similar principle, looking for transiting events. And there's a little video clip I'd like to show you. For those of you interested in astrobiology, I'd encourage you to go to the website at the page that's listed here and learn a little bit more. But this will tell us about the TESS mission.
NASA's TESS mission has found its first Earth-sized world in its star's habitable zone. This means the planet, called TOI 700d, has the potential for liquid water on its surface. TESS stares at patches of sky for long stretches, recording light from thousands of stars. Some of these stars have planets that cross or transit in front of them. TESS sees these events as tiny, regular dimmings of the host stars. One star where TESS saw transits is TOI 700. It's a red dwarf about 40% the mass and size of our Sun and roughly half its temperature. One set of transits announced the presence of a planet close to the star, called TOI 700b. Another set revealed a second planet named TOI 700c, a little farther out. The deeper, shorter transit means the planet is larger than the first, and the plane of its orbit is slightly tipped. A final set of transits showed TOI 700d, orbiting even farther out. TESS observed this system for nearly 11 months and saw each planet transit multiple times. Scientists determined that the inner and outer planets are almost Earth-size and may be rocky. The middle world is more than twice as large and most likely made of gas. All three may be tidally locked, rotating just once each orbit, so the same side always faces the star. But most importantly, TOI 700d is within the star's habitable zone. Scientists wanted independent confirmation of TOI 700d, so they monitored its star with NASA's Spitzer Space Telescope. Spitzer saw a clear transit from the outer planet, affirming its existence and improving scientists' certainty of the planet's size. TOI 700d is one of only a few Earth-sized planets found in potential habitable zones. Others include discoveries by Kepler and several planets in the TRAPPIST-1 system. Because TOI 700 is bright and nearby, the planets are good candidates for precise mass measurements by ground-based telescopes. Future missions may also tell us if the worlds have atmospheres, but scientists need to know what kinds of signals to look for. Researchers at NASA's Goddard Space Flight Center created models of the planet to explore its potential conditions. One version is a water-covered world with an atmosphere similar to early Mars, but denser. Another looks like a completely dry version of today's Earth. Both models have vastly different surface temperatures. Light passing through their atmospheres creates distinct signals because different molecules are present. By simulating these data now, scientists can make predictions for real future observations and narrow the range of TOI 700d's possible conditions. We still have much to learn about the TOI 700 system, but thanks to TESS, Spitzer, and the work of many scientists, we're beginning to form a picture of its exciting new worlds.
I like this video because it brought together several of the things that we were talking about just today, including the habitable zone, looking at spectra of the exoplanets, and the ways that you detect them, including transit events. We're going to go ahead and finish up today by looking at the constellations, and we'll save the last couple sections of the book for Monday. We'll also be reviewing the semester on Monday, our last class. So remember, we're learning the summer triangle, and this is one of the constellations of the summer triangle. It is Lyra, or Lyra, the Harp. And I want you to know about the Ring Nebula, which is between the bottom two stars in this squished rectangle here. And the other thing I want you to know about inside Lyra the Harp is that star, that is Vega. Next we have a bird. What kind of bird is it? It's not an eagle. This is a swan. This is Cygnus the swan. It goes by another name as well. It is the Northern Cross. Now the thing I want you to know about Cygnus the swan is that Deneb is the tail of the swan. You can see why it's called the Northern Cross. Here's what's usually envisioned as a vertical bar of a cross, and the horizontal bar looks like a cross. You can also think of it as a swan, with that being the tail, and Albireo here is the head. Fun fact, there is an X-ray binary, Cygnus X1. Right there in the middle is Cygnus the swan. Cygnus X1 has a black hole, which is about 15 to 20 times the mass of the sun, accreting matter from a companion. The accretion disk around that black hole is very hot and emits in the X-ray. And finally, the constellation here is Aquila the Eagle. Aquila the Eagle. And you're going to want to look for this bright star right there, Altair, and that is going to be in this egg-shaped pattern of stars that form the body of the eagle. And then some of the other stars coming off to the side you can think of as the wings and tail feathers. Now, to review the constellations, I encourage you to go and check out the same video that we posted last week. That's going to help you get ready for the constellation section on the final exam. It's called How to Find the Constellations in the Sky, Taurus, Gemini, Cancer, Leo, Virgo, Lyra, the Bears, and more. It's on YouTube. I'm going to put a link right here if you're watching this on YouTube. You can click on that to review the constellations. Okay, I hope you're all doing well, and take care. Thanks for watching the penultimate version of this astronomy lecture series, and I will see you on Monday for our last one. Bye-bye.